did everyone.
Recording. Good morning, and hopefully good morning to anyone who's picking up the recording later on. So, what this course is about is I came to the horrible conclusion that the computing group I work with wouldn't know a weak form if you hit them over the head with it. And this is slightly unfortunate because it's their job to produce software that does that and does it beautifully and really, really efficiently. So I was eventually bullied by some of the people in my group into running something above finite element course. So this course, which will go for some weeks until we decide we've done enough, or you get bored or I get bored, is intended to be a sort of engineering maths course. So this is the maths of the finite element method much more than how to code it. But we will at various points wave hands and skip over the tedious guts of proofs because basically life is too short. And if you're a real mathematician, then you've probably done this in a course already. And if you're trying to get an understanding of how the finite element method works, then glossing over some of the guts of the details underneath will probably actually make it easier to understand what's going on rather than what isn't there. So it turns out that there is a really good course which is taught at the University of Oslo by Anders Log of Phoenix fame and one of the other Phoenix people, Ken Andre, which does basically this. And there it's a computer science finite element course, which is a rough approximation. So I grabbed their textbook and happily discovered that Imperial College has bought from Springer the PDF rights to this textbook. So you could all have it for free, at least those of you who are in the room. So the textbook, which I will send a link out for, so you don't need to scroll this down, is Brenner and Scott, The Mathematical Theory of Finite Elements. And it, in particular, has a really good chapter 0, where they sketch out what happens in the first few chapters. So this is quite a good way of going through a course, where we do it all in a really hand-wavy sense first, so you understand where we're going, but many of the details are incredibly fuzzy, and then we go back over it again and fill in more details. And that's great, and I started going through chapter -1, and I started asking some of the people in my group about some of the concepts you need for chapter 0, and I came to the conclusion that actually, if you've got a computer science degree, and therefore presumably also various other physical science degrees, you don't actually have the maths you need in order to do chapter 0. So what we're going to do in this lecture today is chapter -1, where we're going to attempt to pick up enough of the basic maths of function spaces that we can understand the rest. So a set of notes have gone round, so hopefully everyone has a set of notes in front of them, which I typed up yesterday, last night, and first thing this morning, so I apologize for the mistakes in there. So what's going on? So what is the finite element method? The finite element method is a numerical method for solving partial differential equations. And what are partial differential equations? They are sets of equations for functions over space and time, potentially, but we mostly talk about space. And those functions are related to each other by derivatives. That's what we mean by a differential equation. And so in order to understand the finite element method, you have to understand the mathematical way in which functions are described in the mathematical framework of the finite element method. And so basically that's what we're going to do today. And so you can summarize today as functions as vectors. And if you can understand functions as vectors, then the next bit where we start gluing those together into a finite element method, which we may or may not start at the end of this lecture, will become more apparent. So this is going to be a 90-minute lecture. We'll probably stop for a brief 5 minutes in the middle so that people can go off if they need to and I can get a glass of water or something. But we're going to start by diving in. So this thing that you should have in front of you says Introduction to Vector Spaces, Inner Products, and Norms. So what mathematicians do is they abstract. So they start off with some mathematical objects with very concrete properties, and then they ask themselves, okay, what are the properties of this object which make it like that object? What are the properties of a triangle that make it a triangle? And how do we therefore define a mathematically abstract concept of something like a triangle. And if you're a applied mathematician, what you do is you abstract up to the point at which you get something useful. And if you're a pure mathematician, you abstract up to the point where no one understands it anymore. And hopefully, the applied bit comes before the pure bit. So hopefully you abstract up to the thing you wanted before you start understanding it. And so this applies basically to all of maths. It is the one trick of mathematics. In particular, it applies to vectors. So what we're going to spend today doing is talking about how you can use the concepts that you understand for real vectors in R2 or R3 and apply that to a much bigger class of mathematical functions, objects, and in particular to functions. So here you can treat functions as vectors. And that's really handy because we know how to do lots of operations on vectors, and if you can treat functions as vectors, then all of a sudden all the operations you know how to do to vectors, you can do to functions. And basically, once you can do all those operations to functions, that gives you the toolkit of functions you need in order to do the finite element method and to solve partial differential equations. So the first thing that we can do then is we can actually talk about what are vectors. So, well, a vector is a thing in a vector space. So that wasn't really a very useful step. So it's more useful because we don't actually normally talk about vectors. We talk about vector spaces, right? So we talk about vectors in R2. So vectors on the Cartesian plane, vectors in R3, which is the cube plane. For anyone who hasn't stumbled across this notation, although those of you who I've taught in Earth Sciences will have done for sure, we use this funny R to mean the set of real numbers, and we raise it to a power in order to indicate, so R2 is the plane. So it's a real number this way and a real number that way, and R3 is the 3 space, but mathematically we don't have to identify R2 with a geometric concept. So we can just think of R2 as a 2-dimensional real vector space, and we can think of R3 as a 3-dimensional real vector space, and that means that we can have R anything we like, because we don't now have to think of it in geometric terms. It's just a vector space that's that big. But I kind of begged the question there, right? Because I said, well, it's a vector space that does that. So in true mathematical form, a vector space is a space, which is to say a set of vectors, a set of objects, where the objects act like vectors. And specifically when we say they act like vectors, what we mean is there's a specific list of things that they've got to be able to do. And so that list is on the front. So we'll look at those. So the first one is that I can scale vectors. So we're here going to talk about real vector spaces, which means that if I take a vector x in my space, whatever my vector space is, and I've got a vector x, I can multiply it by a scalar alpha. So at least for this lecture, I'm going to try and use Roman letters, which I may or may not remember to underline, as the vectors. And I'm going to use Greek letters as the scalars. So I can multiply a vector by a scalar, and I get another vector. And for our purposes, those scalars are always going to be real numbers. Strictly speaking, you can define vector spaces over other fields. So we can have a vector space where these numbers are complex numbers, for example, or other things. But for our purposes, it's enough that we do real vector spaces, so we'll do that in order to avoid confusing ourselves. So I can multiply by a scalar. I also have additive closure, which means I know how to add two vectors. So if I could take x plus y, and what add means might be different in different vector spaces. All I'm saying is there is an operation called add such that I can take a vector x and a vector y and add them together. And so, for example, in R2, you know how to do this. So if I have a two-dimensional vector on my conveniently two-dimensional blackboard, and I have another two-dimensional vector, what I do is I move this vector here, and I go to this one, and I get another vector. And this vector is the sum of these two vectors. So I've got an add operation. In all vector spaces, I need an add operation, but it might not be that add operation. But there are rules about how these operations have to work so that the maths of these things look sufficiently like this. So one is that addition is commutative. So addition is commutative means x plus y is exactly equal to y plus x. So that any addition operation definitely has to be commutative. It also has to be associative, and so if I have x plus y plus z, it has to not matter what order I do those additions in. So it has to be the case that x plus y plus z is equal to x plus y plus z. Those of you who are thinking several stages ahead to implementing this on a computer, and if you know a lot about computer arithmetic, you will know that floating point arithmetic on computers is not associative, and this is not true, but it's approximately true, and for our purposes, for the moment, we're just talking about actual real numbers where we have infinite precision. So this is really true in every case we actually care about. And the next one we want is a similar rule for multiplication by scalars. So I don't need to specify the actual rules between scalars themselves, because the scalars are just real numbers, and we know what the rules are for real numbers. So you can always do real multiplication. It's associative, it's commutative, it's linear, everything else about it is lovely. But we do have to care about it when we multiply by a vector. The reason for that is that if I write beta times x and then multiply it by alpha, I haven't done a real number multiplication. Right? I've multiplied beta times x, and beta times x is not a real number, it's a vector. And now I've multiplied it by alpha times that new vector. And multiplicative associativity says that that has to be the same as alpha times beta times x. Now, in the normal case of Rn that you're used to, that's obviously true. Right? So that's not a big surprise, but it's a requirement that that be true in order that we still have a vector space. And similarly, two other operations. What have I done with my eraser? Oh, yes, there we have. Two other operations which are ordinary operations if what we were dealing with is real numbers, but are things we actually have to require if we want to play with vectors, are the distributive rules. So because now, so in real arithmetic, you basically have one distributive law, but we've now got two sorts of objects. So in real arithmetic, you've got scalars, and we've now got scalars and vectors, and so that means that we have two distributive laws. We have one for scalars, which is to say if I have alpha plus beta times a vector, that has to be equal to alpha times the vector plus beta times the vector. And the other version of this is where instead of adding the scalars, I add the vectors. So alpha times x plus y has got to be equal to alpha x plus alpha y. And once again, in the real vectors, that hopefully doesn't surprise anyone in the room. The ones that start to get a little bit more interesting, and one that actually causes a limitation in practical circumstances about what is a vector space, is 0 has got to be in the vector space. So there has to be a vector which we will always label the 0 vector. Now the 0 vector might look like something different, right? Because you don't always have an Rn vector. There has to be a 0 vector. And what it means to be the 0 vector is that 0 plus x equals x for all x in the vector space. Is everyone here familiar with this sort of set theoretic notation? Turn up the top. So what these mean, this upside down A means for all. There's another fun set theoretic notation we're going to use a lot, which is a backwards E, which is there exists. So those are the two quantifiers. And this thing here is a member of. And there's a similar one which is just a cup, which looks like a rounded less than symbol, and that means is a subset of. So this thing is an individual vector which is in here, so it's a member of this set. So for every member in there, so that means that there's a single 0 vector that acts as the 0 vector no matter what you're adding it to, so it's unique.
Will you use that to be a strict subset?
If I'm paying attention, I will use that to be a strict subset, and therefore if I mean a non-strict subset, so the pedants in the room are pointing out that the set itself is a subset of itself. And in a parallel notation to what happens with less than or equal to, if you're being very, very pedantic, then you write subset or equal to if you want to include the set. I'm not even going to promise that I've done that consistently in these notes. It's kind of irrelevant in these circumstances because I struggle to think of a circumstance in anything we are going to touch where you would want to exclude the set itself from the subsets. So you can probably ignore that for all these purposes. The final rule, which causes a lot less trouble, is remember, we haven't at this stage defined at all what it means to multiply by a scalar, because we haven't said what these things are. And so there is one rule that's universally true about multiplying by a scalar, and that is if we take the scalar 1, now I don't have to define what the scalar 1 is, because remember the scalars are the real numbers, so 1 is a really well-defined concept. So 1x, unsurprisingly, has to be x. One of the rules of scalar multiplication. That rule, in conjunction with the other rules about linearity of scalar multiplication, tells you, for example, that if you have the normal real vectors, it had to be like you think it is. Right? You can derive everything you know about the normal Rn vectors from the fact that there are a vector space consisting of 2 reals in, or n reals, subject to these rules. Basically gets you there. So, informally, I've just spent about 10 or 15 minutes telling you that vectors act like you think they do. Right? All that does is formally set down the rule book for what it is vectors have to do. And so we can do some really obvious examples. And the most obvious example is Rn, and I'm not even going to write it up on the board because you guys know how to work in Rn. But the other really important example, and the whole reason we're doing this whole sorry story of vector spaces, is that functions are also vectors. So, I've written up here functions on some domain to R. Unfortunately, I've only been provided with a pen and a 2-dimensional whiteboard. So I'm going to represent my domain of some arbitrary dimension as a 1-dimensional interval, because then I can draw the functions. And so all the functions defined on an interval, no matter how psychopathic, so all the functions which are continuous nowhere and jump around randomly, and also all the ones that you normally think of as functions that are useful to work with, if you take that whole set of functions from this to the reals, so we're not omitting functions that go infinite here, you have to be bounded everywhere, that's a function space. And so this is the subtle point, right? If you haven't thought about this before, that thing is a vector. Right? The point in the function space is the whole function. And so I can have 2 of them. I can, hey, let's go into Technicolor. I can have that one, and I can have that one. And now I've got an addition operator. Right? The addition operator is, at every point I add the function. So the red one plus the blue one gives me a function which goes up higher here, and then is something close to 0 here, and then is a little bit higher here. So that's add. I can also multiply by a scalar, right? If I multiply this function by a scalar, it stretches out. And so actually it's fairly straightforward to convince yourself, if you go back, that all those rules on the front apply. All the normal rules about adding 2 things. So if I wanted to say alpha outside of x plus y, so this thing is x, this thing is y. So what that's saying is I can either scale the black thing, or I can scale each of x and y first and then add them together and make it to the same place. And that's really obvious. Right? So it just falls out that all of these things do that. There are other interesting function spaces. So all the functions I've drawn up here are continuous. And it turns out that the continuous functions are also a vector space. So now the continuous functions obviously have all the same operations as the previous function. So that was already obvious. The only thing you then have to think about is the first two rules. We have to be closed under addition and we have to be closed under scalar multiplication. So you have to convince yourself that if I multiply a continuous function by a scalar, it's still continuous. Well, that's true. And if I add together any number, any finite number of continuous functions, then it's still continuous, and that's true. If you let yourself add together infinitely many continuous functions, then you can get into trouble. In the finite space, it works. And so that I've skipped a page here. Back. So those are kind of, that's really happy. So that motivates why it is that we're interested in vectors as functions. Because when we looked, everything we already knew about functions made them act like vectors. So I've just introduced, without telling you, one of the really important concepts for function spaces that makes finite element work, which is the concept of a subspace. So a subspace is a subset of a vector space. So I take all my vectors and I take some subset of them, and it's a subspace if that subset is itself a vector space. And so what that actually means in practice, because those points come from the same space and we've got the same operations on them, all of the rules for function spaces obviously trivially apply, except for the ones about closure. So except for the rule that says, if I've taken a couple of random points and I add them together, is the point I get after that still in my subset? That's not obvious at all. And similarly, if I take one of my points and I scale it, is that still in my subset? That's not obvious at all, right? So the subsets of a vector space which are subspaces are exactly the ones where addition and scaling doesn't take you outside of the space. Now this is the first thing that I told you that you didn't kind of know already. So let's illustrate this a little bit with the easy case. So let's stop worrying about complicated things like function spaces. So incidentally, a function space is just a vector space in which the vectors are functions. Right? It's just a naming thing. If we take, here's R2 and here's my origin, there are some interesting cases that tell you a lot about what it means to be a subspace. So the first one is if I take a straight line through the origin in R2. So that is a subset of R2. Points on that line are all points, they're all in R2, it's a subset. So I can add points on the line, I can scale them and so on. So what does it mean to scale them? Well, if I am, another color, if I'm a vector in R2, I look like this. Those lines are actually coincident. If I was a better at art, I probably wouldn't be an applied mathematician. And what does it mean to scale this? So if I scale it, it grows and shrinks along that line and possibly goes negative. So that works, right? So scaling works. Similarly, all the points that are in my subset point in this direction. So if I add them up, according to the normal rules for vector addition, I can't change direction, right? Any sum of vectors that all point in the same direction still points in the same direction. So for the lines that go through the origin, addition and multiplication are closed. So the set of points that goes through the origin along a straight line, and goes in both directions, but I can't stop here, because I could always multiply my vector by -1, then I'd fall out of my function space. So, but the infinite line that goes through the origin, any infinite line is a subset. Sorry, it's obviously a subset, it's a subspace. Okay, now let's look at the other case, which is a straight line which does not go through the origin. So this is the easiest example of something which is not a subspace. And the most straightforward way of pointing that out is just to do scaling. If I take some point in here, so that this point in this space is that vector, and Now I scale that vector by any number other than 1, I get a value of the distance on the line. It's similarly the case that if I take any two vectors on here and add them together, I will get a point that's not on the line. If you were paying attention earlier, it's also kind of obvious in the case that there is no zero vector in this space. So there's, so that's true for, so that's what the set of subspaces looks like for Rn. And so in more dimensions, if we're in R3, all the lines that go through the origin are subspaces, all the planes that go through the origin are subspaces. And to answer the question of the pedants earlier on, of course, R3 is a subspace of R3. The whole plane is a subspace of R2 here as well. Okay, so that's just great and it's wonderful. In the function space case, let's just think about the continuous functions. Right? The continuous functions are clearly a subset of all of the functions, and the continuous functions are a subspace of all the functions. They're a vector space under the same operations as all the functions. And the zero function is a continuous function, and the sum of any two continuous functions is a continuous function. Any multiple continuous function is a continuous function. So therefore we know. Incidentally, you don't need to check separately for the presence of the zero vector, because scaling by zero is the same thing. Right? Zero times any vector must be the zero vector. So if you can scale, then you've got the zero vector. Conversely, if you don't have the zero vector, you can't scale it. So they come out to the same check. Just to indicate that there are interesting functions that don't work, for the same reason as the straight line, the set of all positive functions, so the set of all functions which are positive for any value of x, is not a subspace. Trivial. Because I can take -1 times that function, and I've now got a negative function, which isn't in the space. So, it does happen. Okay. The one really obvious omission from the normal arithmetic operators that we haven't looked at, that I didn't give you in my list of things that a vector space has to have, is any way of multiplying vectors. There were only rules for scaling a vector by a scalar. There were no rules at all for any version of multiplying vectors. So that's quite important. In order to be a vector space, there is no requirement whatsoever that you have a rule for multiplying vectors together. In fact, if you take the space of all functions, it's not very obvious that there exists a rule for multiplying together functions from all spaces, at least not one that behaves. It's using pointwise multiplication, it's not very useful. So, now we're going to restrict ourselves in a bit. We're going to restrict ourselves in a bit to those function spaces on which something that looks like multiplying vectors works. Now, happily, in Rn, in the function space you know everything about, you know how to do it. So in Rn we have the dot product. So if I've got x, y, these two things are in Rn, then this thing is equal to the sum from I equals 1 to n of the ith component of x times the ith component of y. For the moment, in order to try to avoid confusing you, I'm going to always try to remember to put the sum in there. A rule you need to be aware of, because you will see it in a lot of the finite element literature all over the place, possibly even in the book, is something called the summation convention, sometimes the Einstein Summation convention, which says that if I just wrote down two components indexed by the same index multiplied together, that meant I meant to sum of them. That's a convention that exists where we just leave off the summations. But I will try to avoid confusion. I will try to remember to always put the sums in. But anyway, that's not anything you didn't know already. So what do? We do the only trick that mathematicians know. And we attempt to take this operation, we abstract it. And we say, what is it about this operation which makes it a dot product? And then we will try to make operations like that on other vector spaces. And so the terminology that's used and the terminology kind of comes from what happens if you write out the matrices and do the contractions, is the generalization of a dot product is an inner product. And an inner product, which we write for the general inner product this. So an inner product is a function which takes two things in, and it gives you back a real number. Right? Once again, remember that means a real finite number. Infinity is not the right answer. And so this is a function. So this is another piece of notation that you may not be aware of for vector spaces. If I have my vector space, V cross V is the vector space I get by taking pairs from that vector space. So this is what you did when you made R2, where you took R cross R. You took pairs from R. So this is from V cross V, I take two V things, and I get an R out. Now, of course, functions from V cross V to R is a huge range of things, and most of them don't behave anything like a product. So, I mean, in particular, the actually, no, there's probably not particular. The zero function, for example, doesn't really behave like a product. So I can just take any two things in there and give you zero out, and that's a perfectly good function. But it doesn't look at all like the dot product. So what do things that look like a dot product look like? Well, one of the rules is, once again, commutativity. We tend to like multiplication operations to be commutative. Most of them are, although there are exceptions. So if I take two vectors x and y, I want it to be the case that that's equal to the product of y and x. As a side remark, those of you who know anything about complex vector spaces, on complex vector space that's not true. On complex vector space this has to be the conjugate of that. But we're in real space here, so we don't have to care about conjugates. Everything's actually commutative. So that works. We also want something called bilinearity. So you hopefully know what linearity means. Bilinearity means linearity in each argument. So bilinearity means that if I have alpha x plus beta y inner productive with z, right? So that's just a vector because we're closed under those operations. So if I have this vector inner productive with this vector, it's got to be the case that that is equal to alpha times the inner product of x and z plus beta times the inner product of y and z. And I haven't in the notes or here written out that that's also true for the second argument, but you knew that because of the first rule. Right? If I had this expression in the second argument, where you could have just turned the expression around, because that's what this tells you, and then this rule tells you that it works for the second argument as well. So we linear in each argument. And the final rule, which you do already know about the dot product, is positivity. So if I take the dot product of a vector with itself, so the dot product of two different vectors can definitely be negative. If I take the dot product of a vector with itself, that's always a positive number. That's always greater than or equal to 0. And it's only equal to 0 if the vector I put in was 0. So any vector that isn't 0, you take the dot product with itself, it's a positive number. That turns out to be really important. One of the side effects of this is, so if we've got these rules, that any function which obeys those rules is an inner product, in particular, dot product is an inner product. That enables us to define a property that we'll use all the time because it's really useful. And that property is orthogonality. So in Rn, we instinctively, geometrically know what it means for two things to be orthogonal. It means they're at right angles to each other. And we also know what that means in terms of the inner product, which is to say that it means the inner product is 0. So in these general vector spaces, we don't really have a geometric concept, right? Because these vectors could be anything. But we still have an inner product. So we say that x and y are orthogonal if and only if the inner product of x and y is 0. I'm just defining that and leaving it on the ground now. It's going to come up again and again and again when we actually start doing finite element. It's a really, really important property. Okay, so I've been banging on about the inner product case that you all knew about before we even started, which is the dot product. What happens if we go back and start looking at function spaces, vector spaces where the pointer functions? And the answer is that there are inner products, plural, on those spaces, depending on which space you're in. And during the course of the finite element method, we will bump into more than one of those. But there is one which is kind of the base case and the one that turns up all over the place in the basis of the finite element. And it's called the L2 inner product. So mathematicians often call the dot product the little L2 product. And the 2 there comes from the fact, so the dot product is the sum of the squares if you take the norm. So if we go back to norm space, I'm getting ahead of myself because we'll do norms in a bit. And you can do that to any power. So because the dot product is based on squaring, it's the L2 one. And the corresponding one, in some sense, the basic inner product for functions is referred to as the big L2 inner product. So that never causes any confusion whatsoever. And in the simplest case, let's take functions on an interval in one dimension. So I've got a function from A, B, to omega. And this is one of the points at which we turn into an engineering maths course. This is a function which is integrable and its square is integrable. And I am not even going to begin to start talking about the whole hairy set of situations where that's not true. Suffice it to say that almost every function we're going to care about in this course is sufficiently well behaved that it's integrable. Right? It's not a high bar. Lots of functions are integrable. So if a function is square integrable, then the L2 inner product on that function space, so I've got 2 vectors, and I will, when I specifically mean vectors which are functions, I'll probably call them f, g, and h, because it's easier to see what's going on in those cases. So if I've got f and g, and I take the L2 inner product of them, so often, if it's obvious which inner product we meant, because in the context we're in, there could only be one that applied, we'll just write bars for angle brackets for whichever inner product applies. If we're in a circumstance where there's more than one inner product flying around and it matters, we'll write as a subscript which inner product we mean to all the time. So the L2 inner product is the integral over the domain, so the integral from A to B. Sorry, this is a this is a function, right? What do functions do in our limited world? They go from a domain to R. So this is the integral from A to B of f times g times dx. And so you then have to go back and convince yourself that all those previous properties were true and that really is an inner product. Well, the linearity is easy, right? Because the integral is a linear operator. And so because I can multiply these out linearly using distributive law, I can then apply. So if I have the inner product of f plus g with h, then that's equal to the inner product, the integral from a to b of f plus g times h dx, which is equal to the integral from a to b of f h plus g h dx, which is equal to the integral from a to b. I apologize to people at home, I've probably just gone off the screen, of f h dx plus g h dx. If you're sitting at home, that last line is an exercise for the reader. So that falls out just by what you already knew about products. Similarly, scaling falls out. So that's not a big surprise. And the other one you need is positivity. Well, let's take these off here, back up to here. So positivity says that the inner product of f with itself is equal to the inner product of A to B of f squared dx. So f squared is positive, is non-negative at all points, right? That's what it means to square it. And if I take the integral of a function which is nowhere negative, that has to be positive. And if I take the integral of a function which is the integral of a function which is non-zero on any interval is non-zero. So what is the case is that these in this inner product, in this function space, the zero function is actually a class of functions. So it's a slightly more subtle concept. And the reason is that if I have the zero function and I integrate it, I get zero. If I have a function which is zero everywhere, non-zero at a point, I integrate it, I get zero. And I can do that actually at any number of points. So if we want to use this inner product, then the function spaces we're using are the function spaces for which the functions are equal. We say a function is the same function, it's equal, if they're equal almost everywhere. Equal except on a set of isolated points. So it's a slightly subtle point, which will come back to haunt us. But it does work. And if you want to make your life slightly more easy for the moment, you can think about the space of continuous functions. If you just think about the space of continuous functions, it's easier, because if a continuous function is non-zero somewhere, it has to be non-zero on some interval around there, even if that interval is very small, and then the interval is non-zero. Right? So it's only a slightly tricky and subtle point in the case where we allow functions to be discontinuous at points. And discontinuous at points is something that doesn't come up much in finite element. It's a little bit about. Otherwise, you can just think about it as not being a problem. Okay. So that's the L2 product on these functions. Probably most of you did not sign up for your master's projects or PhDs or whatever you're doing to solve partial differential equations in one dimension. Not very many of them are very exciting. So you probably didn't care about this case and you wanted me to tell you what the rules are. If this was some other domain, and that domain is probably now some space of Rn, right? So you're solving a problem in 2 dimensions or 3 dimensions, you've got some space in Rn. And with my engineer hand-wavy hat on, we'll say, let's assume that that's a nice enough domain in Rn. So you're not going to give me a space which is an infinite set of disconnected points or something else which is like that, so that I can still do integrals. And so I need to be able to do the L2 norm, the equivalent thing, for 2 functions in that space. So I need to be able to integrate them to get a number. So I need to be able to say this is equal to the integral over the domain of f times g and yes, well that's fine, because I evaluate f, I get a number, I evaluate g, I get a number. If I want to get even flashier, I have functions from here to Rn. This is wrong in the notes. So now I've got a problem. Because now when I evaluate the function, I don't get a number, I get a vector of numbers. But it's a finite vector of numbers. I know how to take a product of a finite vector of numbers. So at each point, I take the dot product and I get a number back. This is important. We're going to use this all over the place in the finite element method. So if I've got a function from a domain to Rn, the L2 inner product is taken by, first of all, at each point, I take the dot product of the 2 functions. So f of x at some x is a vector, g of x at some x is a vector. I take those 2 dot products together. Remember, the dot product is an inner product, so I'm basically stacking inner products on top of each other. So that gives me a number at each point. I integrate that number over the domain. Yeah.
When you apply a function to a vector, do you take the value of the vector and how do you apply it?
So a function applied to a vector is just a thing where if If you give me a vector, I give you something in the other space. That's just functions, right? That's not use. So if you think about a two-dimensional plane and you have velocity in that two-dimensional plane, velocity is a field from that domain to R2. If you give me any point in that plane, you get back a 2 vector.
So the function has the same dimension as x, right?
Doesn't have to. So it depends what you mean by the function of x, but y does not have to have the same function as x. Right? So if I have pressure in a two-dimensional plane, well, the plane is two-dimensional, pressure is one-dimensional. So now this is one-dimensional, this is two-dimensional. Right? They're not. They don't have to be related at all. Obviously, these things are functions in the same function space. So the size of these things is guaranteed to be the same, so that dot product will make sense. That has to be true by definition. Otherwise, it doesn't make sense to dot product them together. You can't dot product two vectors from different vector spaces. If I ask you what the dot product of the vector 2, 3, 4 with a function is, you have to laugh at it. It doesn't make any sense. So now we can multiply vectors together, and we know how to multiply functions together in at least one way. Right? We pointed out earlier, I could have defined other things that would have enabled us to get a dot product of functions, but this one's not so bad. So that gets us to the end of the inner product section, and we're now going to go on in the last part and do norms in Hilbert spaces and bases. But I notice it's now about 20 past 11, so if I can get Lawrence to hit pause, not stop. Restart? We're good. Okay, so welcome back after the commercials. And so what we got to in the first part of the lecture, we got as far as being able to multiply two vectors together in the sense of an inner product. So in the sense of multiplying two vectors together to get a number out. We haven't looked at multiplying two vectors to get a vector, and we won't. It's not really something which is part of the vector space theory. It comes up if you get into the theory of differential forms, and if you're interested in the theory of differential forms, then there's a very occasional lecture series by Colin Cotter, which is vastly scarier than this one, where you can learn about that. So the next thing that we know we can do with normal vectors in Rn is we know how big they are. We haven't talked about that at all. Right? We haven't yet talked about how long a vector is. But we know that in Rn we can do that. And we know we've got a formula for it in Rn, which is we take the sum of the squares of the components, right? So in Rn, let me put this off and change the sound. In Rn, we have that the norm of a vector is equal to sum from I equals 1 to n of xi squared, the big square root over it. We have lots of mathematical discussions about why there's a square root over there, or I can give you the engineering answer. And the engineering answer is, if there wasn't a square root over there, then suddenly you'd tell me, how long is that vector? And I'd say 10 square meters. And that wouldn't really make a lot of sense, right? So just dimensional analysis tells you that there's got to be a square root in there. Otherwise, it isn't a norm it isn't a length in the concept you understand. So I just slipped up there and used the word. So what do? Mathematicians, we look at the one example we've got, and we decide what is it that's really important about this, and we make a class. So the things which generalize the concept of how big a vector is are called norms. So a norm on a vector is a concept of size. And what do? We define what rules it's got to obey. And we do it inspired by the R2 rules. So the first rule is positivity again. So positivity says that the norm of a vector is greater than 0. It's greater than or equal to 0, but it can only be 0 in the usual special case. Right? The 0 vector has length 0, all other vectors have positive length. That's very important. Linear scaling works like linear scaling. So if I have my vector multiplied by some scalar, and I ask, how long is that vector? Well, that one has got to be the length of the original vector times the scalar. Times the scalar? Oh no. If the scalar is negative, that would suddenly mean that the length would be negative. Times the absolute value of the scalar. Or if you like, times the norm of the scalar. Because R is a perfectly good vector space, and the usual norm on R is absolute value. So the dot product on R is multiplication. Comes down to the same thing. So that's the second rule. The third important rule, and this is the one that you possibly didn't already intrinsically know, is something called the triangle inequality. So the triangle inequality says if I take the length of one vector and I add it to the length of another vector, that is always greater than or equal to the length of the sum of the vectors. So that rule is called the triangle inequality. The reason it's called the triangle inequality, unsurprisingly, comes from our old friend Rn. So what happens in Rn? I write my first vector, I add my second vector to it, so that's the sum vector, and so what the triangle inequality is telling you is that the long side of the triangle cannot be longer in length than the sum of the two short sides. You can extend that to knowing the circumstance in which they get equality. Right? So it's only equal if this thing is a multiple of this thing, because then they line up and they sign up. A positive multiple. We don't mind. So one of the really interesting but unsurprising things here is these properties look a hell of a lot like the properties, particularly this one looks an awful like the properties we require in an inner product space. And actually, you probably, almost certainly, already know that in Rn, the relationship between the usual inner product and the usual norm. So if I'm in Rn, then norm of x is equal to the square root of x dot x. That's the normal rule. So it turns out that's always true. So it turns out that whenever you have an inner product on a vector space, you can create a norm by just defining the norm to be the square root of the inner product of the vectors with themselves. And we're not going to prove it here, but it's fairly simple to sit down and go through the motions and convince yourself that if that's an inner product, then I get the properties I needed. Do the writing out. The only one that's a bit of a pain to requires a bit of writing is the triangle inequality. So the term that's used for this is an induced norm. So the inner product induces a norm on the vector space. That is the norm induced by that inner product. And so what's often, but not always, going to be the case in the finite element method is we are running around taking the norms of things, taking the products of things, and it's mostly going to be the case that in any given context we're using the inner product and the norm induced by that inner product. So they go together. It's the way that the rules work. There is a result of those ones, which yeah, let's do it. Okay, so I've conveniently made my life easier and downloaded proof of the Cauchy-Schwarz inequality from Wikipedia. Yeah, it's not that many lines. So there's an important theorem which gets used in a bunch of places in the textbook, so we're going to need to know about it. And it's a little bit like a multiplication triangle inequality. And it says that if I take the inner product of x and y, that is equal to, is less than or equal to the norm of x times the norm of y. And obviously in this case that norm means the norm induced by this inner product. They have to go together. And what the hell does that mean? Well, we go back to our old friend R2 and we say, okay, so what happens when we take dot product in R2? If I've got a vector here and another vector, and I take the dot product, the magnitude of the dot product is going to be the projection of this guy onto here multiplied by his length. And if these guys line up, then you get equality. Right? If these guys line up, the magnitude of this guy is equal to the magnitude of this guy. And if they don't line up, then this is going to be less. So that's all that this flashy Cauchy-Schwarz inequality says. If we want to prove it, then what we do is we first of all say, okay, it's obvious in the case where either of the vectors is 0. Because if either of the vectors is 0, then both sides of the equation is 0, so it's true. So we can now, henceforth in the proof, we're allowed to assume that the vectors aren't 0, because we're only proving the non-zero case now. So, what we do is we carefully choose a vector. Now this is going to be the only trick in proving almost anything in all the finite element method, and probably actually in most of applied maths, which is what you do is you choose the right function to multiply by, and then it falls out. That's how proofs work everywhere. So the magic function you need to choose in this case is some new vector, z, is equal to, so I'm going to do this for, because I am explicitly plagiarizing Wikipedia here and I don't want to confuse myself and confuse you, I'm going to relabel my vectors the way they've used them, which is u, v, u, v. So I'm going to make a new vector z, which I'm going to call u minus uv over vv times v. So this is not a big surprise number. If you actually look at what he's done here, this thing is the length of the projection of u onto v scaled by v. So he's actually written out what I drew in the board. And he's going to use that. And we're going to take the product of z with v. So z product with v, that's going to be equal to, so z in a product with u, so I'm just going to use the linearity argument here. So that's equal to z, sorry, no z anymore, I'm substituting. That's going to be equal to u times v minus uv over vv times v. Okay, so what that actually means uv minus uv over vv times vv. Ah yes, that's 0. That cancels. That's uv minus vv. So what that proves is that z is orthogonal to v. Z is at right angles to v. Right? Orthogonal means the same thing in any inner product. It just means the inner product is 0. That's useful because it means that the Greeks are going to come and rescue us. They always do. So Mr. Pythagoras is going to get us out of trouble. So what we do is we take we rearrange our definition of z to be u equals uv over BB times B plus Z. So that's just the same thing I wrote down before, I just moved Z and U around to rewrite it. And now, because they're at right angles, we can use the Pythagoras' theorem. So we're going to multiply, so that what that says is if I multiply U with itself, U squared, which is to say the norm of U, and because they're at right angles, Pythagoras applies, that means that I can square this one and this one. That's what Pythagoras' theorem says. So that means I get UB over BB squared times B squared plus Z squared. And
either a square on the left or a square root.
Yeah, you're right. Square on the left. So just multiply by U. Sorry. So the norm is the square root of the inner product of itself, right? So if I take the inner product of itself, I get the norm squared. And so what that's equal to, by the definition of these guys, right? So this thing, and that, so this thing, yeah. And so this is equal to the norm squared. So this is the norm to the power of 4. So that cancels. So what that's equal to, I'm going to drive the camera down now because I'm going to dive off the thing, is the U times V squared divided by the norm of V squared plus Z squared. And that, because of positivity, has got to be bigger than exactly the same thing if I cross off Z. Because Z's a positive number, this is the sum of positive numbers. So that's the norm of U V squared divided by squared. And what was on this side? Remember? U squared. So what do I do now? Multiply by V squared on both sides. I get the norm of V squared, U squared is greater than or equal to the inner product of U and V squared. If I really want to write it down the way I originally wrote it down, I take the square root of both sides. And because we just did that using, so the properties we know of the inner products, that's true always.
Did you take the positive square?
Yes, I did take the positive square root independent. Paying attention earlier on when I said this was the engineering version? Square roots have whichever sign I find convenient. Okay. So now I'm just going to, so I'll give you the critical examples that we know about, right? So we've just spent ages talking about the fact that the dot product induces the normal norm we spent on our end. And really unsurprisingly, there's something called the L2 norm. And what the L2 norm is if I have a function and I take the L2 norm of it, that's just saying that that is the square root of the integral of f squared dx, which is just the square root of the L2 inner product of f with itself. It's exactly the same, it's the induced norm. And to jump backwards, this actually implicitly defines a space. So a vector space, an inner product space is a vector space which has an inner product. And there's a vector space called L2 of any given domain. So if I give you a domain, there is an L2 of that domain. And it is simply the space of functions for which this norm is defined and finite. And so basically what it says is, if you can integrate the square of a function and you get a finite answer, then it's in that space, and that is a vector space because of all the derivations that come before this, and it's a inner product space with the inner product given by this. And that space L2 is going to be the base space for all of finite element. So all the rules and everything else applies in that space. Of course, that's a very loose space without lots of discontinuities. So we're going to spend a lot of our time actually playing in spaces that are subspaces of that space, because we might be interested in all the spaces that are continuous, or in vector land we might be interested in all the spaces that have continuous normal components and so on. And those spaces are all subspaces of L2. Base space is going to be L2 all the time.
Are we going to assume that if we take a norm and we don't say which one it is, that we mean the L2 with the small l?
No.
No. Okay.
Because if I had a function inside there, that wouldn't make any sense. So either there are three possibilities in any given circumstance. Either there is only one norm that can sensibly apply, in which case we'll just write the norm bars, or we'll say which norm we meant, or I've made a mistake and someone should tell me. And those are the only three possibilities which exist. Okay, so I've told you about inner product spaces. I'm now going to tell you about Hilbert spaces, but I'm seriously not going to prove to you how Hilbert spaces work. But I'm going to tell you about Hilbert spaces because it's the piece of terminology that you will see all over this literature. So a Hilbert space is an inner product space which is complete in the norm induced by the inner products. Now, completeness is an analysis concept about series. It means that if I take any convergent series of vectors, so this case means any convergent series of functions, in the case we're interested in, and I take the limit, that limit is also in the space. And all the cases that we're actually really concerned about will be Hilbert spaces, and that's really good, because if you can take limits in the space, it basically means calculus works. That's really important if you want to solve differential equations. I'm not going to go through all of that because basically that would constitute us doing a first or second year university analysis course to get to that point. We're not going to go there. I will very briefly just draw one of the circumstances which could demonstrate why this could possibly go wrong. And that is, imagine I'm in the space of all continuous functions on 0, 1. And I make a sequence which works like this. I take x, take x squared, I take x cubed, I keep going, and I take x to the n, and that's my sequence, and I take that sequence to infinity. And what happens in that sequence is you get tighter and tighter and tighter corners. And so the limit of that space is the function which is 0 everywhere until I get to 1, and it takes the value 1 here, and that's not continuous. That would be a case example of the case. So if I just took all continuous functions on 0, 1, that's actually not a Hilbert space. But happily, that's not a case we're going to need to deal with. So for your purposes, the rest of this course, every time you see the word Hilbert space, you should substitute for this function space in which nothing can possibly go wrong. So basically a rough approximation to what's going on. Okay, the last thing we're going to do in this lecture, and we are going to nail the bases in this lecture, which means that in the next lecture we're going to start by writing a partial differential equation on the board. There will be no PDs in this lecture, is to talk about bases. And so feature number one that we wrote up nearly an hour and a half ago of a vector space is that it's closed under linear combinations. So in the generalized case, that means if I take a sum over I of alpha I times xi, where these things are from my vector space and these are real numbers, then that thing is in my vector space. What closure means. So this leads to a really useful concept, which is a span. So that is, if I take a particular set of vectors, xi, and I take the set of all linear combinations of those vectors, that's called the span of that set. And an immediate consequence of that is that the span of any set of vectors is a subspace. Because remember, what do we need for it to be a subspace? We take the vector space, we have to have closure under scaling and addition. And the span is exactly the set of closures under scaling and addition. So it's trivially true that the span of any set of vectors is a subspace. There's another way around we could look at this, which is I could say, okay, I've got this set of vectors. Could I take one of those vectors out and still get the same span? And for that, we have a very useful concept, which is linear independence. So a set is linearly independent if you can't write any of its members as a combination of the rest. So that means, what do I write here? So that means that if I've got this set here, that set is linearly independent. If I choose xj, then that's not equal to the sum over I not equal to j of alpha I x I. So if I take the set without that one in it, there's no alphas that I could possibly find that would get this one back. So that's linear independence. If a set is linearly independent, then it's in some sense a minimal spanning set for the subspace it spans. And the term we use for that minimal spanning set is a basis. So a basis is a linearly independent set which spans a given vector space. And that given vector space, of course, might be a subspace of some other vector space. That's always true. That's really important because we're going to be manipulating bases like hell for the whole time. That's just the way life works. One really important thing to know is that bases are not unique. There is not the basis for Rn, for example. Trivially, that's true because I could take this set of vectors and I could choose a set of non-zero alphas and I could scale all the basis functions by any of those alphas and I'd still have a basis for the same space. I could also manipulate them in other ways to get other bases. So it's not the case there's a unique basis. It is the case that the size of the basis is unique. So we call the size of the basis of a function space the function space's dimension. The number of basis functions you need to span the whole space is its dimension, and that is an extended positive integer. So it's a positive integer, possibly including infinity. And in fact, different sizes of infinity. Countably and uncountably infinite. We're not going to go into those. But it really matters because the motivating point for doing all of the discrete versions of PDE methods, so finite element, finite difference, and so on, is the fact that the space of even continuous functions on even the interval 0, 1 is an infinite dimensional space. So you need an infinite number of basis functions to describe all the vectors on there, and that's seriously inconvenient if you, like me, have a finite-sized computer. And so the whole story about what we're going to do with the finite element method is we're going to attempt to solve the problem in the right subspace and choose a subspace which is finite dimensional so that we can fit it in the computer. And so I'm not going to draw all this out now, but if we took the functions, for example, to make our life convenient, on the interval minus pi to pi, then a big class of functions on that space, certainly all the continuous ones, but actually quite a lot of the discontinuous ones as well, are spanned by the Fourier basis. So they're spanned by sine x, cos x, sine 2x, cos 2x, sine 3x, cos 3x, and so on. And those of you who've done undergraduate engineering maths will have done Fourier transforms at some point, and they're based on exactly on that spanning set. But that's an infinite spanning set, right? If you want to get all the functions exactly, you have to take n all the way up to infinity. You can cut n off at a certain point, and you get a finite dimensional subspace. And if you do spectral element methods, then those are really based around that concept. Sorry, spectral methods. Spectral element methods are somewhat different, but very close. So that's true. It's also true, and you do know this, for Rn. Okay, so let's just take R3. In R3, we normally call the most usual basis that we use, but remember, we could use another one, but the conventional basis we normally use in R3, we call I, J, K. And we know what they mean. They point in the X, Y, and Z directions. And so we can write any X in R3 as Xi plus Yj plus Zk. Of course, we don't normally bother to write it out like that. It's far too tedious. What we actually write is X, Y, Z. And this is generally true for function spaces as well. So if we've got a finite dimensional function space, then if we've chosen a basis, we can represent every point in that function space by a list of numbers, which are the list of coefficients of the basis functions. So what we'll be doing all the time, whenever we've got a vector space, and usually it'll be a function space, is we'll be choosing a basis, which we normally call Greek letters in the range phi, psi, those sorts of letters. So we'll have a set of basis functions, and we'll be writing our vector as the sum over all the basis functions of that many coefficients times the basis functions. And so those of you who have implemented the finite element method and have seen what goes on inside a field is basically a big long list of numbers, because a field just stores the coefficients of all the basis functions. And that's exactly the same as what happens in R3. So this is why, so we're sort of coming to the end of the lecture now, which is good because we're running out of time. This is why it's we had this lecture. This is the whole point of the exercise is that if we think about functions as being points in a vector space given the right inner product and the right norm, then things we know about vectors, like the fact that we can represent vectors as a list of coefficients for basis functions, works for functions. And doing that and using the properties we've seen earlier, so the concepts of orthogonality and the Cauchy-Schwarz inequality, and sometimes the Triangle Inequality, enables you to demonstrate that the finite element method produces answers which approximate the actual solutions to partial differential equations. It enables you to get properties of those, so things like how good the approximation are. In some circumstances, enables you to prove that the solutions exist and those sorts of things. And we're going to dive through a bunch of that in the next few weeks. So I'm going to stop there. It's about 3 minutes to 12, so I will yield any questions anyone thinks that might be useful to have before we switch off the recording. And otherwise, I can also take longer questions. Yes?
Should the basis be orthogonal necessarily?
Oh, that's a really good question. So life is really wonderful in many circumstances if your basis is orthogonal. However, it's frequently not possible or convenient. So if I leap ahead a bit and I scroll up on the board the usual basis for one-dimensional piecewise linear functions, so if I only have 4 degrees of freedom, and I want piecewise linear functions, the basis looks like this. There's the first basis function, there's the second basis function, there's the third one, and there's the fourth one. And I now ask, okay, so is phi 0 and phi 1, are they orthogonal? So orthogonal would mean orthogonal in the L2 norm. So that means that is the integral of phi 0 times phi 1 over the domain equal to 0? And the answer is no, because the integral is going to be the area of this triangle here where they overlap. So actually, it's frequently the case that they're not. There are many circumstances in which life is much nicer if they are, and there are spectral element tricks for cheating on your integration to make your basis functions look orthogonal to make your life better. But typically, no. If they were, we wouldn't have to solve mass matrices. We'd be lucky. Are there any other questions? Excellent. So we might kill the recording there.